So, uh, good evening, everyone. We are here with the live session 11. So, in this session, we'll discuss upon the assignment solutions for week 10 and some sample questions on the lecture material for week 11. Right. So, polarization describes the evolution of the electric field vector during wave propagation. So, here the transverse wave, the oscillation of field is perpendicular to the direction of propagation of wave, whereas in a longitudinal wave it is parallel to wave direction. So from this statement we could conclude that transverse component will be the correct one. How many polarizers are required in minimum to determine the polarization extinction of the light source? So it's simple, only one is required. Which of the following is a non-reciprocal device? Right. So apparently, from the lecture materials, the Faraday rotator is the non-reciprocal devices here. So what do we have? According to the Faraday effect, the direction of rotation is dependent on the direction of the magnetic field applied on the conductor and not on the direction of light propagation. Thus, the Faraday rotation is non-reciprocal. So basically, the polarizers or the waveplates are birefringent materials in which the polarization rotation depends on the direction of the propagation of the wave. Right. The extraordinary and ordinary refractive indices of a quarter wave plates are 1.7483 and 1.4412 respectively. The thickness of the plate for a working wavelength of 1550 nanometer is what meter? So we know that the phase retardation we have 2 pi by lambda Ne by m naught d, and for quarter wave plate phi is equals to pi by 2. Therefore the thickness d is equals to 1.55 into 10 to the power minus 9 by 4, 1.7483 minus 1.4412, 1.26 micrometer. So this is the answer will be 1.26 E minus 6, right? An unpolarized light of intensity I naught passes through the two successive polarizers P1 and P2 at the polarization axis of P2 makes an angle of 30 degree with P1. What are the corresponding intensity outcomes from P1 and P2? So according to the Malus law, I equals to I naught cos square theta. So, average value of cos square theta is half, right? So I1 equals to I naught by 2 corresponding to P1, and I2 is I1 cos square 30 degree, which is 3 I naught by 8. So the second option, I1 equals to I naught by 2 and I2 equals to 3 I naught by 8 is the correct answer. A linearly polarized light is incident on a 2 centimeter uh, terbium aluminum garnet crystal with the Wordet constant of minus 41 rad per TF. The magnitude of the magnetic flux density which required to rotate the incoming polarization by an angle of 30 degree is what Tesla. Okay, so just a minute. Sorry for the interruption. So here it will be basically theta equals to VBL, right? And theta we have and L we have. So V is basically theta by VL. 30 by 180 minus 41 plus 2m minus 2, which gives us as minus 0.6385 Tesla. Next, the seventh one, the assertion. The refractive index, the refractive in, the refractive index, the refractive index of anisotropic materials depends on the polarization region. In anisotropic materials, waves with different polarizations travel at different velocities and undergo different phase shifts. Right. So the assertion being the refractive anisotropy depends on the polarization. So it's a true statement that signifies that the refractive index of anisotropic material just thus depends on the polarization. And the reasons for it is that the waves with different polarizations travel at different velocities and undergo different phase shifts. So, undergo different phase shifts. So, it justifies the assertion, which is the correct reason for the statement of the above mentioned. What will be the polarization of the transmitted light from a half-wave plate if the incident beam is left circularly polarized? So if it goes by half-wave plane, it just shifts by pi by 2 and gives us the right circularly polarization. So these are the this was polarization scheme and polarizers. So this one justifies quarter wave plate, right? This one justifies the half wave plate, and this one justifies Faraday rotator, and this one justifies the linear polarizer. So third option would be the correct one. Suppose you are given a source that is circularly polarized. What will be the orientation of the transmission axis of the analyzer to get maximum output power at the detector. So for the circular polarization, the two orthogonal electric field components are equal in magnitude and 90 degree out of phase, as we know. So when one of the field components is zero, the other is at maximum and vice versa. So at the analyzer output, we will get a constant intensity irrespective of the analyzer angle. So any of the analyzer angle will give us a constant maximum output at the detector. So any one of the above will be the correct answer. So with this, we have solved out the assignment questions for week 10. Now we will do some sample questions based on the study materials of week 11. Right. So a linearly polarized optical wave travels along the direction of the optic axis. The appropriate parameters for the phase modulators are 9.6, N0 2.3, lambda equals 633. So find the half-wave voltage. So V by is lambda D by R N naught Q L, which gives us a 633 by nanometer, 9.6 picometer by V into 2.3 cube. Right. So by solving this, we'll get the answer as 5.38. Right. The three-wave mixing is called so because which one of the options is the correct one? The three incident fields with frequencies W1, W2, and W3 mixed with each. The three-wave mixing is not possible with focus effect. Two incident W1 coupled with visually. So obviously the third option is the correct one, as when C is generated with W3, it interacts with W1 and W2 to generate W2 and W1 respectively, thus giving W3 is W2 plus W1, which is mutually coupled. Right. Now match the following. So these are the say like figures, and we have to solve for these. So this one will be optical frequency conversion rate. 2 will be optical parametric oscillation. 3 will be optical parametric oscillator, and 4 will be optical parametric dot conversion. So according to this, we'll get C as the correct one. So find the ratio of the propagation length to crystal width of a lithium niobate modulator shown in the video given the operating wavelength of one refractive index. So this will be basically L by D lambda R N naught Q, and its V pi is 1064 nanometer and 30 picometer per volt into 2.3 into 2.4, thus giving us the value as 1.214 into 10 to the power 3. Right. So this will be the correct answer for this one. So I had this I had this three to four problems, like for 4 to 5 problems for week 4, as it was a quite easy week, and also the week 10 assignment questions were quite pretty straightforward. I guess you all facing no problem regarding the uh, lecture materials or the assignment problems. So if you face anything, you could just write in the Google groups, or you can just join in the next session and ask your doubts regarding it. Right. So I hope you don't have any problem. In the next week, we'll just wrap up with the week 11 solutions and sample questions for week 12. So if you have any doubt regarding anything for in this course, you could just join in the next session and ask me, or you could just join in, just write your doubt in the Google groups. Right. So, okay. So today I've just covered the assignment solutions for week 10 and sample questions, 5 sample questions for week 11. So, okay. Thank you.